In this video, we're going to be talking about function transformations in abstraction, and in particular, how they pertain to Toolkit functions. Today, what we're going to do is state transformations acting on Toolkit functions, given its equation. As a reminder, if you forget all of the Toolkit functions, or even some of them, that's totally all right. You're going to want to go into the 1.1. I would just honestly go into the PowerPoint slides and take a look at the last I think it's around 10 or 11 slides. I go through each of the toolkit functions and just kind of explain how they work and give them name and definition. Then, if I give you transformations acting on a toolkit function, you should be able to tell me its equation. Now, this one tends to be one that students grapple with a little bit, so really make sure that you take some time with this one, determining whether or not a function is even, odd, or neither. Okay, and I'll make sure that you know when we get to this particular objective, because this is where, again, this is where students tend to struggle. So first, we're going to start with shifts. Shifts is what's called a rigid transformation, meaning that it changes the function, it transforms the function, but it preserves its shape. So given the tables of the function f of t and g of t, we're going to write g of t in terms of f of t. So what I really want you to observe here is that if I take the t values between f and g, nothing happens. But if I look at the y values, we see that something happens. In particular, that if I were to move from f to g, what I needed to do was subtract 2 from each of the associated y values. So the way I would get to g of t is I would take f of t, that column, and subtract 2 from each of its entries. Now, what does this look like on a graph? So let's suppose I graphed both of these functions. So here's f of t graphed, and here's g of t graphed. So as I subtracted 2 from each of the y values, what I want you to observe is that what I've done on the graph is effectively grabbed a hold of the graph and pulled it 2 units down on the y-axis. We call this a vertical shift. And we would describe this as 2 units down. And what yielded that was by taking f of t and subtracting 2. So we see the 2 is represented here, 2 units. And then where does the down come from? That's going to come from the sign. Okay. Now, if you notice, I've changed the tables f of t and g of t only slightly. See if you can discern the differences between the two. If you observe the change in the t values, you're correct. The y values never changed. But the t values, that should say no changes in y. So the t values did in fact change. I added 1 to each of them, which means if I wanted to get to g of t, I needed to subtract 1 from the f of t, the t values from f. Now, what does this mean on the graph? So as a reminder, we've got f of t minus 1 is going to be g of t. And there's my f of t graphed. And now we have g of t. So what happened? Well, as I subtracted 1 from the input, I moved the graph over to the right 1 unit. We would call this a horizontal shift. One unit to the right. Okay, now this is interesting. To the right is where the negative comes into play here. This is counterintuitive. You would think if I see a minus 1, it would go to the left, but it's actually going to be operating in the opposite direction. Okay. Now, here's the basic notion of all of the different transformations that can be represented. So let's start with shifts. The values in this type of function that give me my shifts, we have h, which gives me my horizontal shift. If h is negative, then I'm going to move to the right. Again, this is counterintuitive. But if h is positive, I'm going to move it to the left. My k value also represents a shift, and that's going to give me a vertical shift. I'm either going to be shifting up or down. If k is negative, I've shifted it down. If k is positive, I've moved it up. Now let's talk about the a value. This a value is a multiplier on the outside of whatever function we decide to have. Keep in mind that an addition on the inside of the function is going to be my horizontal shift, and an addition or subtraction on the outside of the function, when I say outside, I mean like to the y values, that's going to be a vertical shift. Okay, so now the a values, what can the a value do? Well, there's vertical dilation. If a is bigger than 1, it's going to be a vertical stretch. If a is in between 0 and 1, it's a compression, which now begs the question, what happens if a is negative? Well, if a is negative, then we're going to be reflecting the function about the x-axis. I'm going to be showing you all of these. Okay, so right now I'm just defining them all, and I'll tell you it would be probably in your best interest to have this written down just as a reference point throughout the rest of the video. Now, what does b do? B serves as horizontal dilation. If b is bigger than 1, it's going to be a compression. If b is in between 0 and 1, it's going to be a horizontal stretch. If b is negative, it's going to be a reflection about the y-axis. We see that a and b are similar yet opposite. Okay. So let's start with this function here. What we have here is a cubic function. And the thing that gives away the cubic part of it is that guy there. This is a toolkit function that has some shifts acted upon it. So let's start with the -2. What does the -2 do? Well, since the -2 is going to serve as the h value, it's going to be on the inside of the function and its addition or subtraction. That means I'm going to be shifting it. And in particular, since this is negative, it's going to be a horizontal shift 2 units to the right. Okay. Now let's talk about the +4. What action is the +4 performing? Well, I know that the k value is equal to 4, and on the outside, since it's an addition, it's going to be moving up 4 units. Okay. Now, what does the graph of this thing look like? If I graph the blue line over the red one, this is the transformed function. This is the transformed function. I see that I've really just grabbed a hold of the initial toolkit function and just pushed it 2 units to the right and 4 units up. Go ahead and state the transformations on this function. Just as a frame of reference, this is our exponential function. This one's not as obvious, but I'm going to start with the toolkit function of 2 raised to the x power. This +1 is technically on the inside of the function. This +1 signifies that the h value is 1, and I've shifted it 1 unit to the left. The k value is -3. This signifies that I've shifted the function 3 units down. So here's 2 to the x +1. We shifted it 1 unit to the left. And then -3, we shifted 3 units down. Now, we are going to talk more particularly about these types of transformations in 4.2. But for right now, I just want to introduce them. Truth be told, all of the transformations that we're going to be doing throughout the course are going to be pretty much exactly the same. Now we're going to talk about vertical and horizontal reflections. So with a vertical reflection, you could think of this as a reflection over the x-axis. A really great demonstrable function for this would be if I had an absolute value function, and let's suppose I reflected this over the x-axis, look like this. Okay, the vertical componentry would reflect. I really like the language about the x-axis. I feel like it's a little bit more clear. And the way that that happens is by negating the y values. That's going to be a negative multiplicatively on the outside of the function. Right? This is not shocking. We've already talked about this on the slide where I outlined all this. Next, we have the horizontal reflection. That's going to be a reflection about the y-axis. A really great example of this would be a square root function. So here's my square root function. If I reflect this thing about the y-axis, it's going to look like this. Okay. The way that that happens is by negating the x value as the input of the function. Okay. So let's reflect that square root function both vertically and horizontally. Vertically, remember that means across the x-axis. And then this is across the y-axis. I really don't like that language. I really love the across the x-axis and across the y-axis. I feel like it's the most succinct. So first, we'll reflect it vertically, which means across the x-axis. Each output value is going to be reflected over the t-axis, which is really just x. Okay, and so just as we saw before, we're reflecting about here. So that's going to make our graph go from here to there. Okay, this is what the equation would look like. All right. Our negation on the outside of the toolkit function. Now we're going to reflect this thing horizontally, which is across the y-axis. Right. So now I'm going to take this thing, spin around this axis. And what that's going to do in the equation is make the negative attached to the input variable, which in this case is t. Now we're going to talk about even and odd functions. This is the third objective. This is where things get the most complicated. And it's not complicated in its procedure at all. The real thing is, honestly, students forget what they're doing. So here's what's really happening. A function is even if this relationship happens. What this basically means is the function is symmetric about the vertical axis. And what I'm actually talking about here is, let's suppose f of x was something like this, just as a frame of reference. Let's suppose this was f of x. What f of negative x means is I reflect this thing about the y-axis. Well, if I took this graph and reflected it about the y-axis, I've changed absolutely nothing about it. So when these things are actually the same, this is what we call an even function. Now, when is something an odd function? So this one's tricky. So a good example of an odd function is this guy. So this is f of x. Here's what we'll do. First, we'll reflect it about the x-axis. All right, so first we reflect this thing about the x-axis. And then we end up with this. Now we reflect it about the y-axis. So we take this thing, we reflect it about the y-axis. If these graphs are the same, if I get back where I started, this function is what's called odd. We call this symmetric about the origin. Let me kind of spell this out. Let's suppose we have this function here. Is this even, odd, or neither? Here's the way that we would go about discerning this. First, I'm going to check for evenness. So I'm going to go ahead and put a negative x in everywhere I see an x. This is going to be a composition. So you see here, everywhere that I saw an x in the original function, I went ahead and put a negative x in its place. Now from here, I actually just did some algebraic computation. Negative x cubed, well, that's just negative x, negative x, negative x. These negatives cancel. I'm left with a negative, and then x, that's x cubed. And then 2 times negative x, that's negative 2x. So what I want you to observe here is negative x cubed minus 2x is not the same as x cubed plus 2x. They are not the same. So this tells me the function is not even. Now, just because it's not even, that does not mean that it's odd. These aren't like integers, right? If a number you give me that's an integer is not even, then certainly it's got to be odd. It doesn't work that way. We need to check evenness. So now here's what I'm going to do. I need to find out what negative f of negative x is and see if this value takes me back here. So what I'm going to do is take this value that I already computed here and just negate it. So now I'm just going to take a negative and distribute it through to this answer and see if it takes me back to the original. And I end up with x cubed plus 2x, which is exactly the same thing. This function now leads me to, well, it now proves to me that this is an odd function. Okay. Now, the way that, again, as a reminder, let's suppose this thing actually ended up giving me something like x cubed minus 2x. Since these aren't the same, you wouldn't say that it's even, you would say it's neither, okay? So just because a function's even, well, okay, just because a function's not even, that doesn't mean it's odd. And just because a function's not even and not odd, well, that doesn't mean anything. It just means that it's neither. Truth be told, more functions are going to be neither. It's kind of hard to come up at times with specific examples of even or odd. Now we're going to talk about vertical compressions. So a vertical compression is going to be, well, a dilation in general. We're either looking at a stretch or a compression. The k value that's out front as a multiplier, just the value. I'm not talking about the sign. The sign tells me whether or not I reflected about the x-axis. If the value is bigger than 1, the graph is going to be vertically stretched. If it's in between 0 and 1, the graph is going to be compressed. Now, if it is negative, then what we need to do is look at the value and the sign. If the sign of the graph is negative, we know we reflected it about the x-axis. If it was like, if we had a k value of like -3, then what the negative would tell me is it's reflected about the x-axis. And the 3 would tell me it's vertically stretched. And the language we would use is by factor of 3. That's the language we would use. Okay. Pardon the poor stacking of the animations here. I'm going to start with this absolute value function. And the reason I know it's an absolute value function is because that's going to be my base parent function. So what am I doing to this thing? First, let's address what the negative does. What the negative is going to do is a reflection about the x-axis. So now in the blue graph, we see that I've reflected it about the x-axis. That's negative absolute value of x. Next, let's address the 2. What is the 2 going to do? Well, that's a vertical stretch by a factor of 2. So we see it's basically kind of mashed in from a vertical standpoint, sort of pulled farther away. And then the +3, that's going to be a vertical shift 3 units upwards. And so this is my final resulting graph. Just as a highlight, this is going to be my final resulting graph. Okay, so now I gave you an equation. You made a sketch of that graph based on its transformations. Now, what I want you to do here is state all of the transformations and make a rough sketch of what it would look like after all is said and done. First, I want you to observe that we're looking at x squared. That's a quadratic function. So we're going to have a quadratic parabola. The 1/3. What's the 1/3 going to do? Since the k value is in between 0 and 1, what we're going to be doing is a vertical compression by a factor of 3. So it's going to make the graph effectively wider. And now what's the +1 going to do? The +1 is on the interior of the function. So what this means is the h value is 1. So I'm going to shift it 1 unit to the left. And this is my resulting sketch. It doesn't have to be perfectly accurate. This is just a sketch. Now we're going to talk about horizontal compressions. I'm going to be completely honest with you. This is not going to be a huge emphasis in the course. It's important to see it, and it's important to discern it, but this is not going to be like a giant focal point of this particular topic. So horizontal stretch compression, it operates kind of in an inverse relationship to vertical stretch or compression, which makes sense. Here, if the k value is bigger than 1, it's going to be compressed, whereas vertically it was stretched. Here, if the k value is in between 0 and 1, the graph is going to be stretched. And something I want you to observe is the way you'd express this is as reciprocals. So where you would normally say, vertically stretched by a factor of 2, that's equivalent to saying you're horizontally compressed by a factor of 1/2. Okay. In the same ilk, if you had a k value that's negative, what that just means is a reflection about the y-axis. Okay. So let's suppose we had something like f of negative 1/2 x. So the negative here would mean reflection about y-axis. And then the 1/2, that would mean, so the 1/2 is going to be stretched. So we would say a horizontal stretch by factor of, well, what's the reciprocal of 1/2? 2. Boom. Horizontal stretch by a factor of 2. Okay, so let's take a look at an example. What I need you to do here is state the compression that took place from g to f of x. In the initial drafting of the textbook, there actually was a typo here, so I had to go back in and fix it. What I want you to observe is particular coordinate points. So look at f of x. Since f of x ends at this point here, 6, 4, g of x is going to end at 3, 4. It should be a 3, 4. Then here we see the x values have been compressed by 1/2, because 6 times 1/2 is equal to 3. So I also want you to notice that g of 2 is equal to f of 4, and g of 1 is equal to f of 2. Okay, so let me draw that out a little bit. So g of 2, right, is 4. Well, f of 4 is also equal to 4. All right, g of 1, well, that's at 2. G of 2 is equal to 2. So it's almost like we took each of those x values and cut them in half to get from f of x to g of x. Okay. Now, given this graph below, what I want you to do is make a sketch. Be very careful in the way that you go about this. There's some very subtle little nuance that I want you to notice about the b value here. So first, in making this sketch, you needed to discern your transformations. First of which, you're going to factor out that 1/2 inside of the function. So what I'm going to want to do here is ultimately get a set of parentheses. But I need to set the parentheses up such that if I distributed the 1/2, I would get back to this thing. So now what the question becomes here is, what should this term be? Well, what number, when I multiply it by 1/2, gives me 1, which is what I want here? Here it's going to be 2. So after I factor this out, I should end up with this line of algebra. Now from here, the transformations are clear. This 1/2 on the inside, that's my b value. That's going to tell me a horizontal stretch by a factor of 2. Okay, just as a reminder. Okay, the k is in between 0 and 1, so that is stretched. So we've got my horizontal stretch by a factor of 2. I shifted it 2 units to the left, and I shifted it 3 units down. The order in which you do this is, it's important, but it's not. I would work from the innermost parts of the function and go from there. So first, we're going to horizontally stretch by 2. Done. Now we're going to shift it 2 units to the left. We did that here. So notice here, you could look at like kind of this. I like looking at this point here, the topmost peak. I'm going to move that over to -2. Okay, that's what we've done here. So we shifted it 2 units to the left, check. And now we're going to shift it 3 units down. So now this peak was at 2. It's going to go 1, 2, 3, down to -1. And there we go. Okay, this is the full transformation here. So what we've done at this juncture is, if I give you an equation, you should be able to discern the transformations, list them, and you should be able to make a rough sketch of the graph. Now we're going to go backwards. Let's suppose I gave you the graph and you needed to figure out the transformations. So the first thing you would do here is discern that this is actually going to be a cubic function. Now, the way a cubic function looks before I do anything to it is like this. So you'll have, let me go ahead and draw that in a way that's actually remotely accurate. So this is what a cubic function looks by default before I do anything to it. You do need to have these shapes memorized. Now there's a few things I want you to notice here. I've got a cubic function, so I know it's going to look the equation is going to look something like this. Now, here's the things I want you to acknowledge. We definitely reflected this about the x-axis because you see this is the default shape and this is the shape that we're given. So it looks like this was absolutely reflected about the x-axis. You could say the y-axis as well, but for the sake of these problems, it's much easier to think of this in terms of x-axis reflections. So since I've reflected this about the x-axis, I'm going to need a negative a value. I don't know what the a value itself is, but I know it's going to have to be negative because it's reflected. I'm going to shift it 3 units to the left because we see by default that point in the middle, this kind of like saddle, is supposed to be at 0, 0. But here we see it's at 3, -2, which means I definitely moved it 3 units to the right. And since it's also at -2 and it's supposed to be at 0, 0, I see I shifted it 2 units down. Okay, great. Now here's the trick. What is this a value? Did I vertically stretch or vertically compress this graph? It's not 100% obvious just by looking at it. So here's how I'm going to go about finding that particular a value. What I'm going to do is I'm going to choose a coordinate pair and choose one that's not this guy here, because if you think about stretching and compressing this thing, this point is actually never being stretched or compressed because it's in the center. Let's look at this coordinate pair. The coordinate pair here is 0, 2. I accidentally have the answer here, my mistake. My x value is going to be 0. My y value is going to be 2. I can now solve for my a value. And I think I've already done that with my arithmetic. Bloop, bloop. It shows my coordinate pair 2, 0. Geez, sorry. It's a tough thing because sometimes you make mistakes and you say things wrong, and then you are faced with the issue of, oh my gosh, should I redo the video from scratch? To which you say, no, I would make this mistake in class, and I wouldn't say, let's start the whole lecture over. So there you go. So what I'm going to do is plug this 0 in for my y value and plug this 2 in for my x value, and I'm going to solve for a. I'm going to use order of operations, start by subtracting 2 and 3, add the 2 to both sides, and after I solve for a, I end up with 2 is equal to a, so now I know this value here is 2, and this is my final equation. If this notion of transformations is kind of blowing your mind at first, this is going to sound weird, but I need you to be patient. We're going to be talking about this a lot throughout the course. So if you're not getting it 100% this first time around, that's okay. You need to be really functional about this. So I think if you're getting this around 80 to 90%, you're in great shape. But we will be addressing this particular idea in later chapters. I would go ahead and get started into the homework, and good luck.